All right, welcome everyone to another exciting week of statistics and probability. We're going to actually talk about categorical data. Um, but first, we need to finish up last week. I don't think we finished bootstrapping from last week, although if you worked on the lab, it's likely I think the lab had you doing some of this, but worth taking a few minutes to walk through an example. So bootstrapping is a kind of a strategy first introduced by Efron in 1979. There's a link to his paper if you're so interested. Um, and the idea here is to attempt to estimate the sampling distribution by using our single sample, right? So let's maybe it's worth stating again, right? So the big topic from last week is the central limit theorem. And what is the central limit theorem? It is saying that if my sample size is large enough, the distribution of the center, typically the mean, of lots of random samples of that sample size will approximate the normal distribution, right? And so we looked at some examples, right? So as we take more and more samples of size 30 or more, typically, it's what the textbook says, we'll relax that assumption next week. But for now, if sample size is 30, we can use, then the sampling distribution is going to be close enough to the normal that we can use the 68, 95, 99% rule to get our standard error. Right? Really useful. But, as we'll see later at the very end of the semester, right, Bayesians kind of criticize that procedure because it's like, well, we never see the sampling distribution and there could be error and you're also leaving out kind of prior information. But whatever. That for now, that's the way we're making that inference. What Efron suggested is like, well, what if I just sample from my sample over and over, and I could actually sort of estimate or actually have data to estimate the sampling distribution. How he makes this work is when he does this resampling process, he allows replacement, right? And so each time we do this, what's going to happen is, so if I have a data set, or, if I have a sample of size 30, right, I'm going to take random samples of 30. And if I didn't do replacement, I essentially would be shuffling my data and I'd calculate the mean and I would get the same thing every time. But what Efron said is, well, no, I'm going to allow replacement. And so for each sample, I will have some observations that appear more than once and some observations that don't. But I'm going to do this lots and lots of times, like 1,000 or more times. And it has some interesting and cool features. One is we're going to see it, sort of also approximates the normal distribution. It also has the feature of kind of diminishing the impact of outliers. It sort of kind of squashes it. And we'll also see it allows us to get standard errors for metrics that we don't have well-defined ways of doing it. So there are some packages in R to do bootstrapping. I actually wrote a bootstrapping package for propensity score analysis because I think it's pretty powerful. But we're going to go through. It's actually in a lot of cases it's pretty trivial to just code it up yourself. You're going to see a lot, like in the predictive modeling world, bootstrapping is very widely used. It's a way of us to get standard error estimates for things like model accuracy or model fit, right? So we can take bootstrap samples and sort of, so if we're going to say, this is our model fit, great, we get a specific number, but we often want to have some kind of range and say, well, obviously that might not be exactly that, but where do we expect it to be? The bootstrap is a great way of getting it. Okay, so we're going to start with the same population we did last week. So we have a uniform distribution where values between 0 and 1 can occur with equal likelihood. I have 100,000 observations here, right? And the mean of our population is 0.4988. So pretty close to, 0.5. Right. And so as like last week, we're going to just take one random sample of size 50 here. And this is what our distribution of our sample looks like. And so to do the bootstrap, right, I'm going to at first initialize a vector of a length 1,000, right? I'm just picking I'm going to do 1,000 what are called bootstrap samples. Now, as an aside, in practice, what I often do is start with smaller bootstrap samples because, it could take time to run this. And then when I'm sure it's working, then I make that number bigger. 1,000's a pretty good place. Sometimes you can go to 5,000. You go much more, you're not gonna, you're just wasting processor time. But, at least 1,000 is kind of a good rule of thumb. So now I'm going to loop through this vector. And for each one, right, I'm taking a sample from my sample, right? So remember, samp1 is a vector of length 50, right? And what am I going to do? I'm going to sample 50. And if I did only this, right, I would just be shuffling my data. And then when I calculate the mean, I would have the same mean every time. But what the bootstrap or what Ephraim showed is like, if I put this replacement equals true or place equals true, right? Some values will be there more than once, some not at all. But like I said, I'm going to do this 1,000 times. And so each time I'm just saving the mean here. And here I could see here's the first 6 observations. So I got a 0.52, 0.59, 0.55. So I'm clearly not getting the same. Oh, I didn't put the mean there every time. And then if I just plot it, this is what the distribution looks like. So this is the distribution of means from my bootstrap samples. So we often call this a bootstrap distribution, a bootstrap sampling distribution, right? So it's meant to mimic this, the sampling distribution, for which we don't actually ever really see. We just kind of know that it kind of exists out there if we could take an infinite number of samples from our population. So from here, right, so how do we get the standard error? Well, remember, what's the standard error? The standard error is the standard deviation of the sampling distribution. Well, here we just have a distribution. So what we can do is the bootstrap distribution is an approximation of the sampling distribution. So let's just take the standard deviation of our distribution, and I want a 95% confidence interval. So that's why I'm using 1.96. Right? If we remember, if we go 1.96 above and below 0 on a normal distribution, that's going to capture 95% area under the curve. So here, this would be our 95% confidence interval using the bootstrap. Okay. And then, as you see, it's not a lot of code to do this, and it's pretty powerful. This is where it really gets powerful. Is it's not just for means. Like maybe you're working with financial data that's highly skewed, right? And so instead of, in the finance world, we often use medians instead of means. So on this slide, everything's the same except this bit right here. I just changed mean to median. So I'm calculating the median. So this vector is a distribution of medians, but I can get a 95% confidence interval from that. And that's great. That's something you can report. Now I kind of have a sense of not just of where it is, but like, the range of where my possible values could be. So the bootstrap, really, really powerful, fairly simple in principle, but it just is tremendously useful in a lot of different ways. So let's pull to this together, and then we're actually going to end up kind of reviewing again, because when we talk about categorical data specifically, we're going to see a lot of these things come up. But we introduced a lot of different distributions last week. And so, of course, the first is we could have a population. It doesn't have to be uniform. I just, picked uniform as one. It could be lots of different ones. And if you go into the Shiny app, you can pick some different ones, right? So we start with this notion that there's a population out there and we want to know something about it. So how do we know something about it? Is we take a random sample. So here is one random sample of size 30, okay? And I shaded this so that the shaded area represents 90, so 95% of the values fall in that shaded area, right? So if we just used a sample and we went, 2 standard deviations above and below, certainly capture the mean, but that's a pretty wide kind of area. So from there, what we know is, well, if we were able to take lots and lots of random samples, the sampling distribution is going to have a normal distribution. It's going to be centered on the population. We don't know the population mean, so we're going to use the sample mean. So the mean for my sample was like right here, and we know the standard error or the standard deviation of this red distribution is equal to the square root of the standard deviation of our sample over n. Okay, so now the shaded area here in the sampling distribution covers 95% of the area. Again, I'm still using 95%, but this is where we get the standard error, right? The standard error comes from this red line. And then lastly, we could do a bootstrap sample. So this green distribution is the bootstrap sampling distribution from that one sample that's it kind of in blue here. So we can kind of see the relationship of all of these. So the bootstrap is, again, an approximation to the sampling distribution, but we can see it's pretty close in terms of width, and it's centered in the same area. So that's kind of how all these things kind of fit together. Questions about this? All right, well, there'll be more opportunities. So let's dig into categorical data. Oh, geez, I should have started with announcements. So I was going to jump to another slide. So for those, if you haven't already noticed, the midterm should be up now. It's 20 multiple choice questions. It's due by Sunday at midnight. You may use your book and notes. It's whatever. We just expect you to do the midterm yourself. Don't consult with anyone else, other students, spouses, whatever, significant others. Please do it yourself. Hopefully it's not going to take you a lot of time, but you probably should set aside an hour or two. My recommendation is very soon, either tonight or tomorrow morning, you can open it up and you can see all 20 questions and, get a sense of what we're asking of you. And you can come back to it. You don't need to do it all in one sitting. I'm gonna kind of punt on this second item, other than to just say if you're encountering missing data, whether it's in the labs or next week we'll introduce the data project. I think it's perfectly fine to just remove rows with missing values, although that's in practice that's not really what you want to do. There's some other good stuff out here. I may post. I have a slide deck on missing data that I'll post as kind of supplementary material that if you want to do something more appropriate using either the mice package or Amelia, that's there. And just another note that lab 6 and 7, we're going to use the Infer package, which is kind of fits into the tidy models framework, which is sort of I think, quickly becoming the de facto standard of doing predictive modeling in the R community. And so Infer tries to fit in that same framework, kind of consistent with what if you're using dplyr and the ggplot kind of way of things. So I just wanted to make sure you have a link to the reference manual for that. All right, so let's start with an example. So we really just talked about quantitative variables last week, but oftentimes we're going to do surveys. And so in the first example we're going to look at is a question that I think was on the GSS, and it asked people, the goal of this question was to kind of get a sense of where Americans are in terms of understanding causality or proper, randomized control trials. And so the scenario was given to respondents that there are two scientists who want to test a high blood pressure drug. One scientist suggests is giving the drug to 1,000 people with high blood pressure and see how many experience lower blood pressure. The second scientist says he wants to give the drug to 500 people with high blood pressure and not to another 500 people with high blood pressure, and then see what the difference at the end. So which is the best way to kind of evaluate this drug? Of course, everybody in this class should get this question correct. It's right, 500 and 500, 50-50. We're going to randomize people so that we can kind of compare the outcomes between the two groups. So when this was actually given to Americans, this is the response. So there were 670 respondents, 571 got it correct, and 99 got it incorrect. Just as an aside, in the next few slides, we're going to use phrases like probability of success and probability of failure, and we may use it a lot as we go through. Success and failure we don't mean to infer or imply value to those. but we're going to have two probabilities and we need to label them as such. In this case, it so happens to be success or failure, right? It's a correct answer or incorrect answer, but sometimes it's not. It's really the difference between a 0 response and a 1 response, a false or a true, okay? Just to clarify some of the language. So like last week, we have a parameter of interest, which is a proportion, right, for the population. But of course, what we have is one sample, right, which we represent with the little hat to indicate that this is a sample proportion versus a population proportion. So in terms of setting up our problem here, right? So we want a point estimate and we want some margin of error, right? When we talk about proportions, we tend to use margin of error, but it's essentially the same thing as the standard error. We called it standard error. When we talk about proportion, we talk about margin of error. So if you're following the polls now as we enter the forever lengthening season of election seasons, you're going to see a lot of polling going on, and they're going to talk about margins of errors. So the margin of error, right, is of course, we don't have standard deviations when we're talking about proportion, so we need to do a little bit differently. So the formula for the margin of error or the standard error is the probability of success, right, times the probability of failure over n, and then we take the square root of the whole thing. This is the standard deviation of the sampling distribution for proportions, right, for proportions. And this, here's the central limit theorem again. It's essentially the same. What we're saying is as our sample size is larger, the distribution of proportions, right, given all those random samples is going to approximate the normal distribution, right? So proportion of samples is going to approximate the normal distribution. The mean is the proportion. And the standard error or the standard deviation of that distribution, or what we're going to call the standard error, is given by this formula. Okay. First condition is the same. We have this condition, and it's sort of the condition for pretty much all of our sampling procedures that we're going to do, is that each observation is independent of each other observation. Okay. These were random sample of 670 random Americans. How one person responded doesn't inform how the other person responded. So we're good to go there. When we talk about the normal distribution, we're kind of looking at large enough sample sizes as a general rule of thumb. N greater than 30 is what's often used in textbooks. So here we're going to tweak it a little bit. We need to say we need to have at least 10 successes and 10 failures. All right. And that ensures, like, if our proportion that we're trying to estimate is like 0.95 or 0.03, we need enough of both occurrences for the distribution to stabilize. All right, so going back to our survey, here's what we're given. We know that our N is 670. Our probability of success, if you will, is 0.85, right? This is a random sample, so we're good to go. We have 571 who answered correctly and 99 incorrectly, so we meet the success failure condition. So we're good to go. So now it's just an algebra problem. So we're going to take 0.85 plus or minus 1.96, right? So we want a 95% confidence interval, probability of success times failure over n. And so we end up with a confidence interval of 0.82 to 0.88. So what are we saying? We're 95% sure that the population, or the proportion of all Americans in the population who have good sense of testing a drug, is somewhere between 82% and 88%. All right. Going back to national polling, I want you to start paying attention. If you're reading any of the news articles or watching the news, they're going to say, in the latest poll by whatever, Siena seems to be a big one, right? They do a lot of political polling. In a national poll of, X or N, right? Pay attention to what that N is. You're going to find it's going to be somewhere between 1,000 and 1,100. And why is that? Because pollsters, for whatever reason, have landed on 3% margin of error being a good place to be in terms of accuracy. And in the next slide, we'll explain a bit why. So, if you want to specify a margin of error before you do your sampling, well, what do? Well, is it just becomes an algebra problem. So we know we want our margin of errors to be 0.03. Now, we're going to assume a proportion of 50-50. Why is that? Because 50-50, when we do that product of success and failure, is going to result in the largest numerator. If we use anything other than 50-50, the numerator is going to be smaller. So this is the most conservative estimate when we're in the middle. So if we do that and we substitute it out, n needs to be approximately 1,068. So if you sample, if you have 1,068 respondents, you're going to have a margin of error no larger than 0.03 or 3%. What if we want the margin of error to be smaller? What if we want to have 1% of margin error? I want to be more precise. Well, we can, do the same algebra and we find out that, well, we need almost 5 times as many respondents to reduce our margin of error by 2%. Right. So in a world where getting people to respond to surveys can be expensive and time consuming, right? 3% is good enough because we can do 1,000 to do nearly 5,000 is a lot more work and they just don't do that. Um, so great. So that's a single proportion. What if we have two proportions? So this is another an adaptation of a question on the GSS, which asks folks whether or not they think the melting of the polar regions will have an impact on, or will global warming have a big impact on the melting of the polar regions. And so the GSS is sort of a sample of Americans. So we could see we had 680 respondents. Then the survey was also given to students at Duke University. So the 105 students there gave it. So we have these different proportions. So the question we want to ask is, is there a difference in Duke students versus Americans in how they perceive global warming, right? That might be the question we're trying to ask. So our parameter of estimate's a little bit different, right? We're interested in the proportion of Duke minus the proportion of US. And of course, we have a sample, so we're going to work with our sample estimates. So not a whole lot different here, other than we need to account for the fact that we have two sets of proportions because we have two groups. So the standard error estimate is going to be a little bit different, right? So we're still using success times failure, but we need to do it for both groups, and we're going to add it together and take the square root. So this gives us the standard deviation of the sampling distribution for two proportions. Okay. In terms of conditions, we'll start with number 3, right? Success failure, we need at least 10 and successes and failures in all the groups. Not a problem here. So independence within groups is kind of similar, right? These were random Americans, random Duke students, knowing one response to the other. The other assumption that's a little bit different, we have this additional one, is independence between groups, right? So we're saying knowing something, whether or not somebody's in one group, doesn't inform the other. Now, I'm going to point out, and at the end, I'll show an example of we are actually technically violating this assumption in this, because Duke students are also Americans. So if I do a random sample of Americans, I could potentially get a Duke student. Okay. So Duke students are actually a subset of the larger group. So this is technically a violation. But it turns out if that subgroup is really small, small proportion of the total population from which they come, it's not that big of a deal, right? So, there's, I don't know what the 300 million Americans, and we have, I don't know how many Duke students are, a few thousand. It's a very, very tiny percentage. So we can sort of ignore it in this situation, but it is something you need to be aware of. And at the end, we'll show how big does that subgroup need to be relative to the large group before it will actually impact the estimate. But we're going to move on. Okay. So we're actually going to dichotomize our response here. So we're just going to say a great deal and not a great deal. So we have our proportion of success is going to be for US 454 divided by 680, which is 0.668. And we're going to take the 69 over 105, which gives us 0.657. And so from here, we're just substituting into our formulas, get our standard error. You could see for the point estimate, we're just taking the difference of these two scores. all this through, and we end up with a confidence interval, a 95% confidence interval of negative 0.1 to positive 0.08. So the difference in the proportions is somewhere between negative 10 and 8%. And because 0, right, if we're going to set this up as a null hypothesis, and 0 is in that range, that's a possible answer given our confidence interval, we would fail to reject the null hypothesis that there is a difference between Duke and Americans. We don't have evidence that their perception is different. So far, so good. Oh, I lost my, oh, there's my chat window. Okay, I don't see anything, so we'll move on. So the next one, the next kind of scenario we have is where we have count data, right? And I find this a pretty interesting study, particularly if you're interested in gambling and things related to gambling or games of like that. So in the late 1800s, biologist by the name of Frank Raphael Weldon, um, so he, pretty famous biologist. He's founder of biometry, and founding editor of Biometrica, which is still one of the top statistics journals in the world. Observed or wanted to know, right? Or he noticed that 5 and 6s seemed to come up more often than other numbers on dice. Okay. So he went about, and I'm going to presume he had grad students because this seems like something I would have a grad student do. Roll a dice 26,306 times and record the number of times 5 and 6 come up. I cannot imagine how long it took him to do that. But anyways, he did it. And he observed that, right? And so here's actually the responses. So he observed that 5 and 6s came up more. In 2009, somebody at the University of Chicago, Labby, tried to repeat this. But of course, in 2009, he built, let me skip ahead. He built a machine to do it. And so here's his little machine that kind of shuffles the dice. It pauses for a second, so it takes a picture, and then had software to actually process the images. So Labby in 2009, using a machine, it still took him 6 full days to get the same number of samples that Weldon did a century before. So it's just mind-boggling to me. Anyways, I'm sorry. So this is the results of what Labby had. So the question here, right, is given what given this observed data, right? So here's what I think this is what Labby observed. So he got 53,222 ones, all the way through. How different is that from what we would expect? And we kind of call this kind of a measure of model fit, right? Because we have an expected way for this data to appear, and we have observed data, and so we're comparing our observed data to what we would expect. And it turns out the metric we're going to introduce here in just a moment is a metric used a lot in evaluating predictive models, or lots of types of models, because oftentimes with models, we can have expected outcomes from our model, and then we have the actual outcomes from our observed data, and we often want to compare those two things to see if they're the same, to see if maybe our model is doing better or worse or in some other way, right? So if you look at the expected column, it's all 52,612, which is simply 315,672 divided by 6. That's how we get that. We would expect the same number of 1s, 2s, and 3s. Of course, we didn't observe the same number, but the question is it far enough away for us to suspect there's something wrong with the dice? This is sort of analogous to the problem we've been talking about for a while, where, if I flip a coin 100 times, I would expect 50 heads and 50 tails. But if I got 55 heads and 45 tails, I'm not going to immediately scream and say there's something wrong with my coin. But if I got 80 heads and 20 tails, right, probably something wrong with the coin. And so the answer, we're trying to figure out where between those, between 50-50 and 80-20, do I say that's the threshold, right? So that's what we're kind of doing here. Again, null hypothesis testing, we state our null. our null is that there's no inconsistency between the observed and the expected outcomes. So then our alternative is that there is some deviation. Right. And so to evaluate, we quantify these counts. So large deviations would, we would be expected, or I'm sorry, large deviations from what would be expected based on the sampling variation, chance alone could provide evidence for the alternative hypothesis. So this is all called a goodness of fit test. So let's break this down. So I think we kind of had this formula last week in a slide, right? So what's our test statistic? When we talk about a test statistic, we have some point estimate minus some null value. Okay, so I think we introduced this first when we were talking about the coin tosses, right? So the point estimate in coin tosses is how many heads I got, or the proportion of heads, right? And our null value could be 0.5, right? Or if I'm doing 100, right, we could say point estimate is how many heads did I get out of 100 coin tosses? And my null value could be 50, because that's kind of what I expect. I'm looking for something different than 0. Now, as we go through, and particularly next week, we're going to see the null value is often 0, right? In the case of our Duke proportions in the global warming example, right, our null value there could be 0 or would be 0, right? Where our null is that there's no difference between Duke's perception and American perceptions. So a lot of times this gets dropped, but I like to make sure I emphasize that is always there, right? Sometimes you'll see formulas where it's point estimate over the standard error, but that null is there. Sometimes we drop it because it's 0 and then sort of mathematically doesn't matter. But I think it's a good idea for now to always put 0 to be explicit about what your null is, because it doesn't have to be 0. All right. So let's move on. So the test statistic for count data that we're going to use is called the chi-squared. Okay, and so the chi-squared is defined by this formula. We're taking the observed value minus the expected value squared over the expected value. And we're going to sum that for all of our situations, for all of our cases or outcomes. Okay, so K here is the total number of cells. So here's our observed and expected value, right? So for getting 1 on the dice, right, we're going to take our observed minus our expected value, square it, divide it by our expected value. And so for 1, we get 7.07, 2 is 4 point, right, et cetera, et cetera. A couple of things to note, right, because we're squaring, these are always going to be positive, right? And like when we talked about our variance estimate, the further away we get from the expected value, that's going to contribute non-linearly. It's actually going to contribute geometrically as the deviations get larger. This notion of the squaring is going to come up again in like 2 weeks or so when we do linear regression. It's kind of a theme. Sum that all up, and so we end up with a chi-squared, right? So we say a chi-squared of 24.73. Great. What does that mean? Right. So if we think about the normal distribution, right, our test statistic is often, that critical value. We're looking for values like larger than 1.96 or smaller than negative 1.96, right? And where did that come from? That comes from our normal distribution. Once we have a value greater than that or less than 1.96, we're in the area, we're in the part of the distribution where, it's less than, 5%, right? We have 2.5% on each tail. So what we need to introduce is a new distribution type. So this is count data, right? So unlike what we've talked about where normal distributions are symmetrical and they go from negative infinity to positive infinity, theoretically. Chi-squared is bounded at 0. We only have positive values because we can't have negative counts. Counts are always positive by definition. So the distribution has to be bounded at 0. Now, chi-square distributions also have different shapes depending on the degrees of freedom. Okay, so for now, we're just going to say the degrees of freedom is simply the number of cases minus 1. Okay, we'll see next week degrees of freedom in continuous variables, which is going to be, our n minus 1. It's always something minus 1. So here I have a couple of chi-square distributions. So I have this blue one is a chi-square distribution with 2 degrees of freedom, meaning we would have 3 groups, right? Chi-square distribution with 4 and 9. Okay. And so what I want you to notice is like as degrees of freedom gets larger, right? Are when we, so what we're looking for is right. So the area under the area under any of these curves is 1. So what we're looking for is a chi-squared uh, um, value where I would get into 95% of the area. So for fewer degrees of freedom, right, I need a smaller chi-square to capture 95% versus here I have 9. In order to get 95% of the area, I probably have to be way out here, right? So where the chi-square needs to be, or how large does it need to be before me to reject the null hypothesis, is going to be larger given a larger number of degrees of freedom. Okay. So going back to our example here, right? So we had 6, right? 6 dice. So our degrees of freedom is going to be 6 minus 1 or 5, right? So what we're going to do is look at the chi-square distribution with 5 degrees of freedom. And here 24.67 is what we calculated a couple slides ago. Oh, it should be 67, not well, I don't know. This should be 24.73. One of those numbers is wrong, but it's like, just call it 24. Sorry about that. I just first time noticing that. So here I'm looking at the area. So if I go to, let's go to our here. So let me pull this up so we can look at the chi-square. No, no, we could do that. We want to look at p chi-square, right? Because that's our this is going to give us the probability, right? So we're going to have a particular critical value. So I could say p chi-square of 24. But note here, this parameter, I have to give it the degrees of freedom. So degrees of freedom is 5. You can see I get 0.999. So remember what this is. This is giving me the area to the left, right? So really what I want is the area to the right, which is less than 0.001. So it's pretty small, which I think is on the next slide, right? Oh, well, we'll show it in a second. All right. So let's wrap up this dice example. So Labby found that 1 in 6 in his case consistently shorter, and that's because of what was on the opposite side. So it turns out, right, if you think about it, the way dice used to be made and the way they marked them is they just carved out little divots, right? And so whatever was on the opposite side of, say, 1 and 2, which only had like 2 divots, 1 or 2 divots, right, had very little material cut out to mark it. Whatever was on the opposite side had a slightly more chance of occurring because the 1 and 2 sides were heavier, right? So before you take this information and run over to Atlantic City or Vegas, you should know they figured this out. So now they fill in the divots. So the dice are well balanced. So the probability of any of the numbers is equally likelihood in gambling, or if you buy dice now. But for a long time, they didn't do it. They didn't know that. Okay, so to recap, right? So for the chi-squared, right, it's a bounded at 0. And so the p-value, is always going to be out on the right tail. So we talked a little bit about one-tail versus two-tail tests. Chi-squareds are always going to be one-tail tests. We're always looking for the area out on the right-hand side. All right, I just want to return real quick to show, where do you need to be in terms of like when you violate that independence between groups where you're trying to compare Americans to, some subgroup. To give an example, I actually encountered this quite frequently from a higher ed perspective. When I was in institutional research, I very often would be asked to compare like retention rates. And if you don't know what retention rates are, it's a common metric used to evaluate that institutions use to evaluate programs. It's the percentage of students who as freshmen returned for a second year, right? So obviously we want that as high as possible. We want students to progress all the way through. And so in higher ed, I would be asked, well, here's my degree program or my school. How does my program's retention rate compare to that of the school at large? And so, well, I have the institutional retention rate. So I calculate the retention rate for some population. Well, that program or that degree program is part of the school, so that they're in both. So then the question going back to my violation, so how big does that program have to be before it's going to influence that overall? I'm not going to go through the R code here. I'm just going to go right to the picture to kind of explain. And we're going to see this 10% rule come up. The textbook also talks about like when we sample, our sample size needs to be less than 10% of the population. This picture is trying to explain why 10%. So this top line here is the probability of, say, of the bigger group. So you can think of this as like this is the proportion of like the Duke students. Okay, and then the green and the red lines would be like the proportion of Americans. Now I fixed it so that the proportion for like say Duke is 60%, and the proportion for Americans should be 55. And so, of course, when I just randomly sample from Duke, there's no problem. I'm not going to get other Americans. I'm only getting Dukes. What this green line is I'm randomly sampling from anybody, which means I could potentially get Duke students. Okay. What the red line is saying, well, I'm going to randomly sample from Americans, but I'm going to explicitly exclude Duke students to force compliance with that assumption, right? So sometimes you can do that. And if you can do that, great, right? Define your populations precisely. So for in my higher ed example, right, I could say, well, this blue line is our retention rate for the master's degree in data science. And this red line is the retention rate for, the School of Professional Studies, excluding the master's in data science. And this green line would be the retention rate of the School of Professional Studies, but I didn't explicitly exclude the Masters of Data Science, right? So what are we saying, right? So if I don't do that exclusion, as I get closer to where that subgroup is like half the size of the total population. So imagine the Masters of Data Science, our enrollment accounts for half the enrollment of the School of Professional Studies. Then the difference in those rates, it's going to be influenced by that other group where it should actually be, 5% different. So why the 10% rule? So if you look at this figure, these gray lines, and we'll talk about this when we get through into the regression area, particularly when we talk about lowest regression. The gray bands around the lines here are approximately 95% confidence intervals. Okay. So you can see when I get up to about 10%, it's just after 10% that there's a significant difference between those two estimates. So that's why we often say, just as a general rule of thumb, if it's less than 10%, we can probably ignore that violation of that assumption. So something you should be aware of. I don't think many people think about this. Many cases it's probably not a problem because you're dealing with smaller groups, but scenarios do occur when you're doing these comparisons of like a total to some subgroup. But if that subgroup becomes quite large, that could be a problem. All right. And thanks, Angela, for putting that link in there. I'm going to put the 1-minute paper in and we'll entertain any questions. Anybody?
So if you go back to the prior visual that you showed, yeah, here. So the orange line is without the Duke students, correct? The US population without the Duke.
Yep. Yep.
Okay. So then, okay, and so why? So that's showing 55%, and Duke students are showing 60%. So what does that mean? Like it's still difference, right?
Yeah. So what I did here, maybe I should explain the code. So I defined some proportions up front. So I built a population here. Actually, sometimes it might be, I should probably just show this interactively. I'll take a minute to do this because I think it's worth it. So if I do this, that's going to define all that. And let me copy and paste this. Okay. So I have this population data frame,
Mhm.
and I can do, so let's look at pop group. So you can see I have 99,000 A and 1,000 B, right? And if I want to pipe that to prop.table, right? So 99% and 1%. So my population, I can say, is 100,000, but 1,000 in my population are Duke students, right? And so sometimes when we do sampling, so if I say sample from population group, and I'm going to say size, let's just do 30. And I'm going to pipe this to table. So when I do 30 and I'm sampling from, there we go. Took me a couple of tries, but here I did a random sample and I captured a Duke student. Right. So that's the problem, because this person is now contributing. So when, but then when I am sampling from Duke, I'm only sampling from Duke. All right. So that's what you need to be careful about. So okay, so that's that. So now let's go back and say, but if I change, so I had a ratio here. Okay, no, right. So here we go. So instead of, population, where did I defined it here. Okay. So, I should have defined it this way. So I'm going to say ratio. So I had 99, but let's say it's, let's go 75. Oops. So I'm going to change this to ratio, and I'm going to change this to 1 minus ratio. Okay. So if I do that, right. So now I have 70, 30, and I'm just doing random samples of size 30, right? I'm getting 11 Bs, but I really want to exclude those, right? So now what I'm saying is now my subgroup is 25% of the total, right? And that's the problem. So when I was at 25%, I'm like right here. So that's going to really influence that overall estimate. And I should point out, I am presuming there is a difference, right? Group A has a proportion of 0.6. The total minus group A has a proportion of 0.55. But if you don't do that exclusion, it's going to influence the estimate. Is that helping?
Yeah, sure. Thanks, Jason.
So I know I talked about higher ed. I can imagine, like if you're in Silicon Valley or any kind of business, right? You could say, here's our conversion rate, right? You're a salesperson. Here's our overall conversion rate, and I want to compare this office to, I want to compare my New York City office to what our national conversion rate is. Well, if the New York City office is larger than 10% of the company's overall sales team, that's a problem, right? In making that comparison. So this shows up in lots of different places. And I just was trying to explain, textbooks generally say it needs to be less than 10% of the population. Why? This is one of the reasons. The other reason is, in any of these random samples, there's technically not even, we're violating the independence assumption, right? So let's look at this class. So right now we have 24 people in the meetup tonight. So I'm going to randomly select one person. The probability of any of you right now being randomly selected is 1 out of 24. Well, I guess I'm including myself. Okay. So I randomly select Naomi, right? Great. I have Naomi. I ask her my question. What's the probability of being randomly selected now? Anybody else? It's now 1 out of 23. Okay. So knowing who was picked first actually changes the probability of who's selected second. But when you're less than 10%, when you're randomly selecting less than 10%, 1 over 24 and 1 over 23 are the difference between those is so small to not really be meaningful. But when we get to 10%, then the first and the, when you get to the 10% mark or greater, well, now those differences in proportions or probabilities of being selected is actually meaningful, right? So as a general rule of thumb, and we could have talked about this, but it would have been hard to explain. This is when, if instead of doing a sampling, when you get to 10%, if you really want to go more, then you really need to do sort of a census, right? And then there's thresholds on the other end. In the Department of Ed, when they do their big studies and they're trying to do census, or actually the U.S. Census, when they do it every 10 years, they expect or need at least 85% compliance in order for the estimates to be reasonable, right? If it slips below 85%, well, then the estimates are going to become unreliable for census data. Then it becomes a sample. But now we're well over 10%, so it becomes a problematic sample. So there's like this, dead zone somewhere between 10% and 85% where it's like, yeah, you got data, but it's gonna be trouble.
I thought every time like you choose the probability doesn't change. So you said for example you're using the Naomi example, right?
Mhm.
If, I mean, were you doing like a situation where once you pick the person you eliminate them from the data set, or because
Well,
I thought
I guess.
everyone had, equal likelihood of being picked, right? Regardless of if the game is okay. I'm picking it. I have a jar with. I have a sample set with students, right?
Mhm.
And everyone has an equal likelihood of being picked.
Yep.
Um, and assuming the person that's picked remains within that data set, is still within the same data set, isn't it still going to be 1/34, regardless of how many times you pick from the data set?
Yeah. So if you're saying you're going to allow replacement, um, so yeah, but then you have, I mean, that's kind of what the bootstrap is trying to do, but you are violating the independence assumption in a different way because unless somebody gives a different answer when they are responding the second time, knowing how somebody responds the first time informs how they would respond in the second time. So you solved one independence assumption problem, but introduced another in that scenario.
Gotcha. So is it like some type of like conditional? Um,
What do you mean by that? I'm not sure if I understand.
so like let's say you have an entire sample set, right? So
Mhm.
knowing some information about the sample set somehow like maybe reduces this like you take a subset of the entire sample set of the entire data set.
Mhm.
Do you mean it that way, or
Um,
just based on like a particular information, right? Like let's say, okay,
not
my sample set is a quick example I'm thinking of is, okay, I have a um a bowl of, I don't know, like wings, right?
Mhm.
A bowl of wings, and um let's say you have like like 5 lemon pepper, and I don't know, the 5 lemon pepper and 20 hot wings, right?
Yep.
And that's your entire data set, 25 wings,
Yep.
right? So let's say you're trying to figure out how many I don't know. Everyone has like an equal likelihood of being picked, right? I'm trying
Yep.
to figure out when would I like what's the possibility of being of like me picking lemon pepper wings, right? So you choose one, you taste it, um, you notice that okay, it's not lemon pepper, right? So that kind of reduces your data set into like a
24.
subset of the entire data set, right?
Yep. You now have 24 things remaining
Yeah.
from your 25.
Okay.
Yeah. So now, given your scenario, the probability of getting a lemon pepper on the second one, assuming the first one was a lemon pepper, is now 4 out of 24, not 5 out of 25.
Yeah.
So there are situations, right? So yeah, so you could put, in that case, yes, you could put the um lemon pepper thing. Is it, I can't remember what you called it. Was a, anyways, you could put it back and then randomly select again and taste, and indeed do that, right? And there are some like examples when I've taught in person, like where I bring little bags of M&Ms and we're trying to estimate the proportion of colors of M&Ms. You could sample and put it back, sample and put it back is one strategy. So yeah, that in that scenario, yes, that's when you're trying to count things like that. That's fine. I'm thinking of a scenario where you're doing a survey and you randomly select somebody to do the survey, and then you randomly select somebody to do the same survey. That's a different, right? The color of one M&M is not going to influence the color. If it's picked again, it can't change its color, right? So,
Yeah.
so
Okay.
yeah, yeah, now, yeah. Yeah, now I want wings.
Thank you.
Yeah, you're welcome. Made everyone hungry. Any other questions? All right. Well, we can call it a night. Good luck on the midterm. I'm sure you're all going to do great. You can send Angela and I messages private if you have an issue with it. Please, when you submit, make sure you're done because it's hard, if not impossible, for us to undo it.
Yep.
Once it's submitted, I think it's impossible. I think Blackboard doesn't allow us to do it.
Right.
So be sure when you click submit. All right. Well, have a good night, everyone. See you next
Night.
week.